Moving on to Unit B of the textbook. Unit A was all about descriptive statistics, so making graphs based on sample data, calculating things like average, proportions, and standard deviation. Unit B is about using that to make predictions about the population. And so this is called inferential statistics. So today we're trying to get a handle on what inferential statistics and the kind of things we're going to try and do here. Chapter 3 is where we're starting off. And chapter 3 is about a thing called confidence intervals, which we'll do a bunch of today. So with inferential statistics, what we're trying to do is make predictions about a population based on sample data. Generally, those predictions are based on some question that we're trying to answer. Like I might want to know, question, what percent of US drivers sometimes text while driving? Maybe I want to know what is the average time one gets some reasonable level of immunity from a COVID vaccine. Average time of reasonable immunity from a COVID vaccine. Oops. What other interesting questions might we ask? I have worked with a lot of students, and it's hard to figure out what one wants to do in the future. So what percent of college students change their major? Would be a question I might want to ask. In the application 3, where we were taking a look at relationships between different variables, there were a lot of different options people picked as far as data goes. One of them that kind of stuck in my head was average income in a state versus percent obesity. And the data seemed to indicate that the higher the average income, the less obese people were in the population. So somehow, maybe we can help people get better jobs, then we can deal with health issues better. The question that we can ask about data like that and projecting from the sample to the population is what inferential statistics is about. And also inferential statistics is about testing ideas we think we have. So for example, something we might test is human body temperature really around 98.6 on average? Or is it different? So we can test things we think we know, and we can ask new questions about that. So the big thing here is we have some population, and populations tend to be really big. State of Oregon, city you live in, a country, college students. And then from that population, we make a sample. Now, we can't access everybody in the population in general, so we have to rely on the sample data. Now, with the sample data, we do things like we find means, right? And remember, our notation for mean was X bar. And so we might grab a whole bunch of people, measure their body temperature, and see what it is on average. And maybe in a sample, we find that average body temperature for a group of, let's say, n equals 50 people is 98.3 degrees Fahrenheit. That's a little lower than average. This is a sample. We might take another sample and it might be a little higher. So one thing we're guaranteed on with a sample is that every sample is going to be different. So we will encounter what's called sampling variability. Every sample will be different. So reviewing some ideas way back from the beginning of the quarter, we have this idea of variability. We have different ways to measure the variability. And I'm not looking at, say, the standard deviation here, the spread in a single sample. I'm thinking about lots of different samples from the population. So I had grabbed this group of 50 people, but there's another group of 50 people over here and another group of 50 people over there. And every one of them is going to have a different average. So there's one average, there's another average, there's another average over here. My hope is that when I took the sample, that the sample was random. Right? We got to have a good random sample. Random sample. And by good, we mean representative, which is like the population. It's not representative of the sample. That means it was biased. And again, the whole idea of collecting a sample and hoping the sample is non-biased, that it's representative, that's a whole nother issue. We're just going to assume we have a sample, it's a good random sample, it's representative of the population. But even if it is a good random sample and it's representative, we're still going to find sampling variation. Every sample is going to be a little different. It's going to have a slightly different mean. And the question is, how do we use that sample data to estimate the population proportion? So right now I have this sample right here. So my X bar, which I'm claiming is 98.3 degrees Fahrenheit, at the moment is my best estimate of the population mean. Now, the population mean, the thing I'm trying to find here, we use the symbol mu for the population means. Remember, that's the Greek letter mu. Greek mu. It's kind of a funky cross between an M and a U. And I don't know it. Now, I'm trying to estimate the population mean. It may be 98.6. It may not be. It may be 98.3, it may not be. So given that I'm trying to estimate it, there's a difference. There's some error there. So anytime, wrong button, anytime we make some kind of estimate based on a sample, we have some kind of error. So we have an error in our estimate. So the actual error would be whatever the population is. Right? And this is some unknown value we're going to call mu minus my sample. That's the known value, X bar. And the difference between those is the actual error in prediction. And the problem here is, one, we will never know the actual population value. That population value in this case is mu and average, but it could be something else like the percent of people who text, right? That population value is in general known as the parameter for the population. So I have this population parameter mu. and I have this sample statistic, X bar, the mean. Let's see, parameter, is that right? So one, I never know what mu is. I'm trying to estimate it. I know I'm probably not right. There's some kind of error in there, and I hope the error is not too big. And that's the other thing here. If I don't know the actual population value, then I can't actually know the error either. So I don't know the actual error. We don't know the actual error either. And just like I can use the sample to estimate the population, there's also a way to estimate my error. So that's one thing we're going to learn today. We're going to learn to estimate the error. So how do we estimate the error? Okay, so a couple big ideas here. We are trying to figure out what's going on in a population, and maybe that's the average, like the average percent of people who text while driving, the average body temperature of a person, the average income in a state. It's hard to get the information from every single individual in any population, whether it's humans or fish or squirrels or something else. So we have to rely on samples. Our sample data, if it's a good sample, we're going to assume it is our best estimate for the population. So that's big idea number one. Since it's an estimate, that means we have some error, and we need to figure out how do we estimate our error. So that's the other big idea here, is how to estimate error in prediction. So a few ideas we'll take a look at today, examples to try and figure this out. Page, please. Texting while driving. And I looked at a recent study from last year on texting while driving, and the claim was that 38% of teens claim to sometimes text while driving. And the data is a little bit more than just texting. So it's being distracted by a phone. So maybe a call came in and they pick up their phone. Maybe they did actually read a text. Maybe they were checking out some, what's that, TikTok, thing. But somehow they were distracted. I'm just going to call it texting here. Now that's teens. Interesting thing that surprised me here was that 56% of adults, which includes some of these, because adults would be 18 years old, 19 years old, so there's some overlap with the teens. Claim to sometimes text while driving. Now, they didn't ask me. I don't know if they asked you. Anyone get a call recently or an email that said, hey, do you sometimes text while driving? And by the way, how old are you? So how do they know this? How accurate is this? Is what I want to take a look at in a little bit. They didn't ask me, and they didn't ask you. So how do they know the accuracy? Now, in this case right here, this is sample data. So let's suppose in this case, I have a sample of size 500. And sample size is usually the letter n. So sometimes we'll see n equals 500. My sample statistic here, and remember the word statistic is just anything we calculate based on data. So a mean is a sample statistic, a standard deviation is a sample statistic. This sample statistic is a proportion. And a sample proportion is usually P with a little hat on top of it. right? So that's P hat. Okay, comment. More experienced drivers feel safer. Yeah, they care enough to multitask. That's kind of dangerous, isn't it? Yeah, there's a lot of cameras that, oh, interesting, insurance companies have access to that, right? Yeah, and distracted drivers, I believe, are a higher percentage of traffic fatalities than drunken driving at this point in the world, which is frightening. So sample statistic, in this case, p hat is a sample proportion. In this case, I'm giving the sample proportion as 38%. So I could say p hat is 38%. Sometimes we state it as a decimal, so we might say p hat is 0.38, but sometimes it's a fraction. Now, I'd have to, the fraction, I'd have to figure out if I wanted as a fraction, 38 is, what is 38% of 500? So I'm gonna calculate that quick to get it as a fraction, because this comes up sometimes. Later, 38%, 0.38 times 500 gives me that 190 of the teens out of 500 reported to text while driving. So I could also state p hat as 190 over 500. So just some terminology that's going to come up. Sample size is the letter n. If we have a sample proportion, that's a p with a hat over it. And then if we have the actual number, like 190 reported texting while driving, that would be x, just the count. So in this case, I can say p hat is x over n, which would be the count of people who text while driving divided by n, the total sample size. So I just figured out x was 190 by multiplying the percent by the sample size. So sometimes we might want to know the actual number instead of the percent. So note, I can rewrite that equation right there by multiplying the n to the other side. So x is p hat times n.
Is there any way that you can lift up the screen, because I can't see the rest of the bottom?
That could be because your Zoom screen is in the way. So that's different on everybody's screen, but I can rewrite that up above. So can you see the p hat equals x over n here?
Yeah.
Okay.
Oh.
Yeah, so there should be a way for you to move your Zoom menu, but it's always going to be in the way somewhere, unfortunately. So I rewrote it as x equals p hat times n. But I'll try to avoid getting close to the bottom. So we'll come back and look at how accurate this is, but let's look at another example. Average baseball player salaries, for example. In Major League Baseball. Oops. So I'd like to know what that is, and it turns out there is some data available to take a look at this. And so let's go take a look at that. So we're going to head over to StatKey. So if you want to try this too, go for it. So this is again a website that accompanies our textbook. And then here, I'm going to head down to the sampling distributions. That's a big topic today we're going to get to next. And the first data set that loads here is 2019 baseball player salaries in millions. So if I grab the data table, this is every Major League Baseball player in 2019. And so if we see a number like 7 for Garrett Richards, that means Garrett Richards made about $7 million just off his baseball salary in the major leagues in 2019. If I look at the summary over here for the population, and again, this is a population because I have every Major League Baseball player that was playing. It's not just a few of them, it's not just one team, it's all of them. So there are 877 baseball players. According to this, the average salary was $4.51 million. Again, if you want to get to this page with me, I will put it in the chat, or you could search for it. We are in the sampling distributions section. So there's the link in the chat. I'll put this in the YouTube description also. 4.51 million. And this would be mu, because I do have the whole population, 4.51 million. So this is the population mean, not a sample mean. So as far as accurate, it's as accurate as the data was given from the Major League Baseball. So we don't have any error in estimation here because this is the actual number. Now what we're going to look at next is, well, what if we took a sample of baseball players? Like we just went out and grabbed randomly 30 baseball players. Would our sample have this exact same value? So we're just going to do a few samples here. I encourage you to try this too. So in this sampling distribution page I'm on here, at the moment it's set to choose sample size of samples of size 10. I'm going to up that to size 30. So I'm just going to click on the 10. So most things are editable here. And it says I can choose a sample size between 1 and 877 because there's 877 people on my list. And I'm going to choose 30 here. And then I'm going to go over to the left here and I'm just going to create one sample. And two things are going to happen. One, it's going to collect all that data and plot it down here. So it's making a dot plot of those 30. So it says I have a sample of 30. The mean of this sample is 3.452. Notice it's a little lower than the mean of the population. I could go get that data table if I wanted. So here's the 30 players I selected. If you do this, you're going to get a slightly different sample. So, and here, what it's plotting is my mean. Notice down here, it's the 3.452, same as the mean there. If I create another, generate another sample, it's going to go and grab 30 baseball players randomly from that group of 877. So I get a different sample. So now that's this one over here. So here's the first one I grabbed, the 3.452 mean. When I point to it, it presents that data over here. If I point to this one here, it says, okay, that one had a mean of 5.885. Now notice both are random samples and neither is exactly the population, and that's what we expect. There's always going to be variability in sampling. Every sample is going to be different, even if it's a good random sample. Now here, again, we're just randomly grabbing numbers. It plotted a new number here at the bottom, 4.669. That's the average of these two samples. I'm going to do this again. I'm going to generate another one sample. This time I got 3.537 as the mean. That's down here. And now the mean of all three of those is 4.292. Now, any individual sample is going to vary greatly, but all of these samples are coming from the population, and the population definitely has a mean of 4.51. And so it turns out the more samples I gather, they're going to end up clustering around this mean. And so this is an important aspect of what we call a sampling distribution. So we're going to build a sampling distribution. I'll try to explain what it means. It's something we got to get used to. So I'm going to generate another one sample, and another one, and another one. Now, instead of just doing one at a time, so far I have 6 of them. I could do 10 at a time. So it went out and grabbed 10 different samples of size 30 from the original list of 877 people. It calculated the mean of every one of them and plotted the means here. So now I'm up to 16 samples. I could do 100 of them. So now I have 116 different samples. Each of these points down here is just the average of the 30 people in that sample. And that would be over here when I point to one of these dots. So every dot here is a sample of 30 people average. So here I have an average of 4.17. I point over here, that one's 6.12. And every time I do this, it's going to be different. So if I reset the plot, so right now my average is 4.5 for all 116 of them. If I reset that and do something similar, 1, I'm still using size 30, 3, 4, 5, 6, and then I grabbed 10, and then I grabbed 100. So there's a new 116, and I have a slightly different mean at the bottom, 4.492. And what I'm trying to illustrate here is the more samples I take, they're starting to hover around this as the center. Will I ever get that as the exact center with random sampling? We'll get pretty darn close. The higher the sample size and the more samples you do, the closer you'll get. Right? If I made my sample size 877, that's obviously the whole population, and I'm going to get the exact same mean, roughly. Now, one thing to note about random sampling, when we random sample from a population like this, it's like looking at a card, putting the card back in the deck, shuffling and redrawing. So we could get the same person again. So there could, even grabbing the whole population, there could be a little bit of variability. All right, so let's go back to 30. And then this time, I'm actually just going to generate thousands of samples. And I'm going to get up to, let's say, 8,000 samples. And notice my computer's slowing down here because that's a lot of calculations. Right, so I just grabbed 8,000 times. We grabbed 30 different numbers from the list over here and found the average of those 30 and plotted the average. So I have 8,000 averages here. Each average is based on a sample of size 30. Whenever we plot a whole bunch of samples, not an individual sample, but a whole bunch of samples, that's called a sampling distribution. So let's make a note of this. So I started with a population here, which we rarely have, so this is a kind of a gift. The idea we're looking at now is a sampling distribution. And a couple of reminders about these ideas here. What's a distribution? A distribution, remember, is just a graph, usually a histogram of some sample data. And then we look at it and say, what does it look like? Is it symmetric? Is it skewed? Is it flat? So I have this histogram of data. Now in this case, it's not just a sample. I'm looking at a lot of different samples. So for a sampling distribution, what I'm looking at now is a distribution histogram. This kind of histogram is called a dot plot, but it's still a histogram. The averages of many samples, each of size 30. And one interesting kind of fact in statistics, and this is related to the probability that we looked at before, if you flip a coin a few times, you're not guaranteed half heads and half tails. But if you do it millions of times, you'll be pretty darn close to half. The more you do, the closer you get to this ideal. The ideal is the population. I'm only looking at samples of size 30. But the higher the sample size, the closer the middle of the distribution is to the middle of the population. So the distribution, sampling distribution, is approximately the mean of the population. Now, we aren't really going to go out to a population and do 8,000 samples of size 30, right? That's not really feasible. But we can take advantage of this idea here with a computer and estimate what's going on with the actual population based on 1 or 2 samples is what we're going to end up doing here. And then this idea of a sampling distribution. So in this case, I have a distribution of sample means, sample averages. So just a whole bunch of them. So that's the idea of a sampling distribution. And it's different, but related to a distribution for a single sample. And just note something here if we look back. The distribution of the baseball salary players, there's a few people that get a ton of money. There's lots of people that don't make a lot, like under $1 million here. And there's a few people who make a ton of money. So this graph right here is skewed right. It's my right side, yep. It is a tail on the right. But notice the sampling distribution is pretty much a symmetric bell shape. Now it does have a slight tail to the right, and that's just because of the extreme tail on this value here. Generally, a sampling distribution is going to have a symmetric bell shape like this. Let's look at a different one on. Which one do I think was interesting here? Players percent internet access in countries. So here we have a population, 204 countries of the world. What percent of the people in the country have internet access? So there's a country where only 2% have internet access. There's other countries where 95% of the people in the country have internet access. But on average, this is kind of a flat distribution. There's about just as many with very little or medium amount, like 50% internet access, or most people have internet access. Now, if we do a sampling distribution, so that means of these 204, let's grab samples of size 30 again. And if I get one of those, so I randomly select 30 of the countries. There could be some repetition here because we're looking at the cards and putting them back in the deck. So I found instead of the average being 54%, the average was about 50% for this one sample. Every time I do a different sample, it's going to look a little bit different. So if I do a few of them, right, this is the idea of sampling variability. What that means is each sample is going to be slightly different. They look different when I graph them. They have different means. But if we go and replicate thousands of samples of size 30, what we should see are a couple of things. One, we should get a bell-shaped curve. And I got this bell-shaped curve here. And two, if I have a reasonably high sample size, and we're going to say the minimum for high sample size is 30. Okay. You could do, we can, so a question came up, is 30 the minimum for the sample size? The answer is no. You could do samples of size 10. Ideally, we want the sample size to be 30 or more to get a good prediction, to get a reasonable margin of error in our estimate, and to have this curve be relatively bell-shaped, regardless of the shape of the population data. But there are some cases where it's just not possible to get 30. So maybe it's some dangerous surgery we're doing on people, and we can only get data on 10 people to try and make predictions about how this might work with other people in the population. So there could be life and money factors that just don't allow us to do a sample size more than 30. If it's an opinion survey, we can easily get thousands of opinions. That's not a big deal. But there's some situations that are trickier scientifically, ethically, where we really can't get big sample sizes. So we're going to shoot for 30 or more, but sometimes that's not possible. I'm just going with 30 because that's like the usual minimum for averages in samples. And the other big thing is that the average of the distribution, that middle that StatKey is giving me here, should be pretty darn close to the actual population middle mean in this case. So here, my 4,005 samples, each of size 30, averaged out to be about 54.559. The actual population number is 54.465, right? So is that close enough? Well, it's as close as I have right here. We'll get into margin of error in just a few minutes. So what I'm looking at here is a sampling distribution. We'll just pause here and then we're going to move on.